All right, so this question is asking us to one, find the total number of squares in the sixth step of this pattern. Identify whether this pattern is showing linear, exponential, or quadratic growth, and also write an expression to represent this pattern. So I always like to start with the total number of items on each step. And so step one, I notice there are 0 squares there. I'm going to use a different color. So 0 squares. Step two, I notice there are 3 squares. Step three, I notice there are 8 squares. I also want to look at the change in the rate of change. So to go from 0 to 3, that is a plus 3. Going from 3 to 8, that is a plus 5. I think I need at least one other pattern to kind of figure out, like one other step to figure out what's going on. So I'm going to go ahead and draw step 4 based on what I can see. So step 4. So it looks like, oh, there's a square, but a piece is taken off. There's a square, but one is taken off. If there was a square here, it was subtracted. So I am guessing that this is a 2 by 2. This is a 3 by 3. So I'm going to suggest that this is going to be a 4 by 4. Oh man, I can't draw to save my life. All right, so we're going to do a 4 by 4. And we're going to leave off 1 square. Bear with your teacher. My teacher is learning to draw. We just are not going to close that last one. So that last one is missing. All right. So it kind of looks like the same. I know mine's a little bit crooked, but hey, such is life. So how many squares do we have there? That's going to end up being 15. So again, let's see what's going on with our pattern. So from 8 to 15, how much are we adding? Oh, that's 7. It's quite clear for us now that even though the rate of change is not constant, there's a pattern with how the rate of change itself is changing. So what do we notice? From 3 to 5, that's a plus 2. From 5 to 7, that's a plus 2. So we can say that this is showing quadratic growth. And what we know about quadratic growth is that there we see squares increasing. So if I look at it, oh, what's staying the same? What's staying the same and what's different? So if I think about it, what's staying the same? Oh, each square loses 1, or each pattern loses a square, loses a square. So I'm going to write that. No. So stays the same. Come on, Mrs. Thomas, get it together. So what's staying the same? Stays same. It says if we're subtracting 1 square. And then what's different? What is different is the size of each square. So what's different when we think about it? The size of each square. What do you mean? Well, the second one happens to be a, let's change this color a 2 by 2. The third one happens to be a 3 by 3, and the one that I drew is a 4 by 4. So we're going to assume that we had a 1 by 1 here, but it was subtracted. So how do we get the expression? Well, if we think about it, we can create a table of values where we can call our step number, we're going to say that is x, and the total number of squares is going to be y. So when it's step 1, we had 0 squares. When it was step 2, we had 3 squares. When it was step 3, we had 8 squares. When it was step 4, we had 15 squares. So what we're seeing is we're subtracting 1, so that's the thing that's consistent. So if we think about the expression, that will produce it. We notice that we're subtracting 1 from the square. So step number squared. And we want to say that our step number is going to be represented by n. So our expression is equal to n squared minus 1. And the 1 is, we're subtracting the 1 square. So if we wanted to find the 6th pattern in this, what we would say, was it the 6th? We wanted to find the 6th pattern, it would be, if we wanted to find the 6th pattern, it would be 6 squared minus 1, so that's 36 minus 1, 35. It would be n squared minus 1.